A phase-shifting transformer (PST), also referred to as a phase angle regulating transformer (PAR), is a specialized type of power transformer used in high-voltage alternating current (AC) transmission systems to control the direction and magnitude of active power flow. Unlike conventional transformers, which primarily change voltage levels while maintaining the phase relationship between the input and output voltages, a phase-shifting transformer deliberately modifies the phase angle between voltages at two interconnected nodes. This unique capability enables transmission system operators to regulate power flows through selected transmission corridors without changing the power generation output. As modern electrical networks become increasingly interconnected through regional and international interconnections, the demand for effective power flow control has increased significantly. The growing penetration of renewable energy sources, expansion of cross-border electricity trading, and increasing network congestion have made PSTs an essential component of modern power systems. The operating principle of a phase-shifting transformer is based on controlling the phase angle difference between 2 points in an AC transmission network. According to the power transfer equation, the amount of active power transmitted over a transmission line is directly proportional to the sign of the phase angle difference between the sending end and receiving end voltages. By increasing or decreasing this phase angle, the PST can redirect active power from overloaded transmission lines to underutilized parallel circuits. This redistribution improves network efficiency and prevents thermal overloading of transmission equipment. Rather than increasing transmission capacity by constructing new transmission lines, utilities can install PSTs to maximize the utilization of existing infrastructure, thereby reducing investment costs and minimizing environmental impacts associated with new transmission corridors. Phase-shifting transformers are generally classified into two main categories: direct PSTs and indirect PSTs. In a direct PST, the phase shift is produced within a single transformer structure where both voltage regulation and phase angle adjustment are integrated into one magnetic system. Although compact, this design is typically suitable for applications requiring moderate ratings. In contrast, the indirect PST consists of two separate transformer units, an exciting transformer and a series transformer. The exciting transformer generates a controllable voltage using an on-load tap changer, while the series transformer injects this voltage into the transmission line at a specific angle. The injected voltage is approximately perpendicular to the system voltage, producing the required phase shift. Indirect PSTs are the most commonly used configuration for extra-high voltage transmission systems because they provide greater operational flexibility, higher power ratings, and improved maintenance accessibility. The construction of a phase-shifting transformer is considerably more sophisticated than that of a conventional power transformer. The exciting transformer supplies a variable regulating voltage whose magnitude is controlled by the on-load tap changer. This tap changer allows continuous voltage regulation while the transformer remains energized, enabling real-time control of power flows without interrupting network operation. The series transformer receives the regulated voltage from the exciting transformer and injects it into the transmission line through specially designed windings. Together, these two transformers create the desired phase displacement between the input and output voltages. Additional components include magnetic cores manufactured from high-grade silicon steel laminations, copper or aluminum windings designed for high current carrying capability, oil paper insulation systems, bushings for high-voltage connections, cooling systems employing oil circulation and radiators, protective relays, gas-operated Buchholz relays, pressure relief devices, temperature monitoring equipment, and sophisticated digital control systems that supervise transformer operation. One of the primary advantages of PSTs is their ability to increase the loadability of highly meshed transmission networks. In interconnected power systems, electricity naturally follows the path of least impedance rather than the commercially scheduled transmission path. Consequently, shorter transmission lines often become overloaded while longer parallel lines remain underutilized. By adjusting the phase angle, the PST redirects part of the active power flow toward these underloaded transmission paths, thereby balancing system loading and increasing the effective utilization of the transmission network. This capability significantly improves transmission efficiency while delaying or eliminating the need for expensive network expansion projects. Phase-shifting transformers also play an essential role in international electricity markets. Many countries are connected through cross-border interconnectors that facilitate energy trading between neighboring power systems. However, actual physical power flows frequently differ from commercial trading schedules because electricity follows the electrical characteristics of the interconnected network. These unscheduled or loop flows can overload transmission lines in neighboring countries and reduce the available transmission capacity. PSTs provide transmission system operators with a practical solution by regulating active power exchanges across interconnections and aligning physical power flows more closely with market schedules. As a result, international electricity trading becomes more reliable, secure, and economically efficient while minimizing the adverse effects of unscheduled power transfers. Another significant application of PSTs is congestion management within transmission systems. Rapid growth in electricity demand, increasing renewable energy penetration, and delays in constructing new transmission infrastructure have resulted in persistent congestion on many transmission corridors. Grid expansion projects often require years of environmental assessments, land acquisition, and regulatory approvals. During this period, PSTs provide an effective alternative by redirecting power away from overloaded circuits toward available transmission capacity. This increases the utilization of existing assets while improving network flexibility. Utilities can therefore postpone major capital investments while maintaining secure and reliable operation of the electrical network. Modern power systems increasingly depend on renewable energy sources such as wind and solar power, whose outputs fluctuate according to weather conditions. These variable generation patterns create continuously changing power flow conditions throughout the transmission network. Phase-shifting transformers support renewable energy integration by directing renewable power from generation centers to major load centers without overloading intermediate transmission lines. They allow operators to optimize transmission capacity utilization while maintaining voltage stability and system security. Consequently, PSTs contribute significantly to achieving national decarbonization goals by enabling higher penetration levels of renewable energy without requiring immediate large-scale transmission expansion. Phase-shifting transformers contribute to both preventive and corrective network control strategies. During preventive operation, a predetermined phase shift is maintained continuously to distribute power flows optimally under normal operating conditions and ensure that the system satisfies N1 security requirements. This means that the network can continue operating safely even if a single transmission line or major component becomes unavailable. During corrective operation, the phase shift is automatically adjusted following network disturbances such as transmission line outages, generator trips, or sudden load variations.